Hello everyone, my name is Ben. What you are watching now is a course on calculus. In this course, I will try my best to make calculus more understandable. And today, this is our very first video. In this video, I will try to do a bit of research on the area under a parabola. Here is the problem. We have a very simple quadratic function f equals x squared. And now I'm doing the area under its curve from 0 to 1. I've already shaded with the purple color and denoted with letter A. So do you have any idea for this? Well, we can see that this area comes with a curly side, right? This curly side makes it a bit different and difficult. We don't know any area formula for this. So we'd better look for some new idea. Like in history, we have a mathematician who introduced a bunch of rectangles. For example, we can build 10 rectangles like this. We divide the whole interval evenly into 10 parts, 10 sub-intervals, and build rectangles on top of them, just like this red one. It stands on a sub-interval and goes up until its top left corner touches the curve, right? With these 10 rectangles, we can then use the total area of them to approximate the purple area. This is basically how the idea goes, but I'm not happy with these 10 rectangles. It seems 10 rectangles are not good enough. We can still see the error, the difference that come between the rectangles and the purple area, right? But lucky again, this method is very flexible. Instead of 10 rectangles, we can build 20 of them. In this case, the error is smaller. And if we build 50, we can see the error is much smaller. And if we keep doing and build 100 rectangles, we can see the error is tiny. It's nearly invisible, right? So this method of building rectangles is very useful. With more rectangles, we can always get better result. The total area will perform better and better. So now let's look at how to do the total area, how to calculate the total area. And we still use 10 rectangles for a simple demonstration. In this case, this red rectangle will be our second last rectangle, will be our ninth rectangle. And we know it's even partition, so the base will be 1 divided by 10. It will be the length of the interval divided by the number of rectangles, right? So it will be 0.1 for all the rectangles, the base. With the base, we can then figure out the sub-intervals that the rectangles occupy. For example, for the first rectangle, its sub-interval will just go from 0 to 0.1, right? And the second rectangle comes after the first one, so it will go from 0.1 to 0.2. And the third rectangle comes after the second one. We can do this one by one. And for the red rectangle, its sub-interval goes from 0.8 to 0.9. Then how about the height? We can see that this red rectangle, its top left corner touches the curve. So this point is also a point that lies on the curve. This means the height will be the function value of this point, the left end point of the sub-interval, right? So it will be 0.8 squared. And this is a very general pattern for all the rectangles. The height is the function value of the left end point of the sub-interval. So we have all the sub-intervals here, so let's just take the left end points and take the function value. So we will get all the heights. For the first rectangle, very unfortunately, it's 0 squared. That's why we can't see the first rectangle. And for the red rectangle, we can see it's 0.8 squared. We have already seen this value. So with the base and height, it's very easy to do the area, right? We just take the product of them. For the first rectangle, its area is 0.1 times 0 squared. It's still 0. And for our red rectangle, it's 0.1 times 0.8 squared. It's this value. With all these areas, we just sum them up and we will get the total. It's 0.285. We know this value is not good enough because the error, the difference that comes with this value is very obvious, right? But the calculation is good. The whole calculation is good. So let's try to generalize this process. And suppose we have n rectangles this time. And this is a very general case. Because it's even partition, so the base will be 1 divided by n for all the rectangles. And the subinterval for the first rectangle, it will go from 0 to 1 over n, right? And the second rectangle comes after the first one, comes immediately after. So it will start here, start from 1 over n to 2 over n, right? And the third rectangle comes after the second one, so it will go from 2 over n to 3 over n. We can easily figure out the general pattern. For the ith rectangle, suppose this is the ith rectangle, its subinterval will go from the fraction I minus 1 over n to the fraction I over n, right? And if this is a very last rectangle, it will be the nth rectangle. We put n in this pattern, we will get the subinterval. It goes from n minus 1 over n to n over n to 1, right? It's just the right endpoint of the whole interval. With the subintervals, we can do the height and still take the left endpoint and take the function value. So for the first rectangle, it will always be 0 squared based on the construction. And for the second rectangle, it will be the square of this value, the left endpoint, right? And for the third rectangle, it will be the square of this value, still the left endpoint. And if this is the general pattern for the subinterval, this will be the pattern. For the height, the square of the left endpoint, and for the very last rectangle, of course, it will be this value, the square of this fraction. And still, base is done, height is done, just take the products of them, we will get all the areas. So now the job is to sum them up. Here is the sum. The first term is the area of the first rectangle, the second term is the area of the second rectangle, and this is the area of the third rectangle, one by one, and this is the area of the very last rectangle. We just put all of them together. Here I also call this sum the left-hand sum, because we use the left endpoint, we use the function value as the height, right? And you can see that I denote this sum with SL. In this video, SL, the left-hand sum, is the total area. The total area is the left-hand sum. And now let's look at how to evaluate this sum. For the first term, easy, it's 0. And for the second term, this is n, this is actually n squared, so we will have a cubic in the denominator, right? And for the numerator, it's only 1 squared here. And for this term, we can see n here, n squared here, so the denominator is the same, a cubic of n. And for the numerator, it's 2 squared. We do this one by one, and we will get a sum like this. And for this sum, we just take the denominator out, take the cubic out. We will get a sum of squares of numbers. 1 squared plus 2 squared plus until the square of n minus 1. It might be a bit difficult for many of us to do a sum like this, so I put a green formula here for your reference. If you didn't know this formula before, don't worry about it, just use it directly. If you have any question, just let me know in the comments and I will try my best to answer it. So this formula says the sum of squares of numbers from 1 to n equals this. But our sum is this. The last term is the square of n minus 1. So what's the difference between our sum and this sum? So this term is missing. So we just move n squared from left to the right. And this will be the result of our sum. And we can see this is n squared but a minus 1. And this is n squared but it's a half, a positive half. So after the subtraction, we will get a negative half, right? So we put this result back in the parentheses and remove the parentheses. We will finally work out a general formula for the total area for the left-hand sum for SL. It says SL equals the fraction 1/3 minus the fraction 1 over 2 times n plus the fraction 1 over 6 times n squared. I'm very happy with this formula. This is actually a big achievement. In fact, with this formula, no matter how many rectangles we have, we can get the total area immediately, right? For example, when n equals 1, this means we use the whole interval as a base. So the left endpoint will be 0, the height will be 0 squared, and the area will be 0. Of course, the sum will be 0. And when n equals 2, the total area is 0.125. And when n equals 3, it will be this value. When we have 10 rectangles, when n equals 10, it's 0.285. We have seen this value before. And you can keep doing, right? You can try any number of rectangles. So basically, you will get a sequence of total area. You will get a sequence of values, and this sequence is endless. If you are happy with 100 rectangles, you can use this value as an approximation of A, right? As long as you accept the error that comes with this value. And if you are only happy with 1 million rectangles, you can use this value as an approximation, right? It's all up to you. We can see that if you use this value, the total area is roughly 0.3333. A lot of 3's are here. So we can see that we have solved the problem. We have solved the problem numerically. We found a numerical solution. For the purple area under that parabola, it equals SL approximately when the number of rectangles is large enough, right? But I know some people are not happy with this solution. They like something exact. They prefer this equal sign rather than this equal sign. So can we just go a little bit further and find the exact value of A? Yes, we can. From this formula and from this sequence of values, we can see that the total area is getting closer and closer to a fraction. And we also know that the total area is getting closer and closer to a number A. A is also a number. So what's the relationship between these two numbers? Are they equal? If you believe A equals 1/3, you have to provide a mathematical proof, right? And that will be the content of our next video. In this video, We just come up with this formula and we use it as approximation of the purple area. And this is already good enough. So I will stop here. And if you guys think today's video is a bit helpful, just give me a thumbs up. And if you have any question, just let me know in the comment section. I will try my best to answer it. Okay, thank you guys for watching. See you next time.